Okay, good afternoon, everybody. So today I'm going to be talking more about pushdown automata, in particular PDAs. So last day we were talking about how we can design PDAs, and we talked about what a PDA is. Now, technically, in some level, I haven't really told you how a PDA processes strings. We've just made a lot of assumptions about how the PDA processes strings. In particular, we've had this idea of having it where the PDA consumes symbols, like some hungry hippo. It kind of goes around gobbling up marbles wherever it could get those marbles. In this case, it's given some string, and the goal is it needs to gobble up all the symbols of the string, and we want to usually have it sitting in that final state, right? That was the idea, is we want to consume all those symbols, and we want to make sure we're in the final state when that happens. But remember, it has all the features of an epsilon NFA. So it means that if, say, you were to transition where there is no such transition in delta, then surely that's no different. It'll be basically like it dies or that thread gets killed. It has that non-determinism aspect of it. So I want to formalize how exactly we formalize what I've been calling a move in a PDA. So to do this, I'm going to introduce something called an instantaneous description. Now, that big fancy name, I'll call it an ID. So what you might ask is, okay, well, why do we need an instantaneous description, whatever this thing is? Well, think about it from the perspective of what we were doing before when we talked about an epsilon NFA. When we had an epsilon NFA, we always had it where the transition function always returned us a set of states, right? Now, here in a PDA, we don't just have a set of states anymore. Now we actually have pairs where each one consists of a state and some information in there, right? It has pairs. So remember, it has a state, and we have information about the symbols that are going to replace the top of the stack, right? So it maybe even pop the stack. So we have this information, and remember, like I said, these two things, even though they're two components of the PDA, we have to have both of them together to describe a configuration of the machine at a given time. They're not two separate things when we describe a configuration of the machine. So I need some way to describe how you move from one configuration of the machine to another, because that's really why we need these IDs. Is unlike before, we don't just transition from one state to another anymore. Now we have it where we have also this stack that's in play. So I'm going to formalize a way that I can say we go from one state to another, but I also have to say some state with some information about the stack to another state with some information about the stack. So here's how I'm going to formalize this. It's going to be a triple, so it has three inputs. So three parts. I should say parts. It has Q, W, and gamma, so that's a lowercase gamma. So Q is going to be the state. W is the rest of the input I have yet to process. So remember, you got to think of the PDA like a hungry hippo. It's going around trying to gobble up them marbles. I'm hoping I'm getting somebody with this reference. If not, go look at it later on YouTube or something. so gobbling up these marbles, and as it gets consumed, this W is going to deplete as this gets gobbled up. So just as a question for you, when I finish processing the string, what should be sitting in W for my instantaneous description? So I'll give you a hint. It's not W. Remember, it's the input remaining to be processed. So when I'm done consuming all the symbols, what should be sitting here in my instantaneous description? Yeah, it's the empty string. Perfect. It's the empty string. So that's something I want you to keep in the back of your mind as we do this. I'll be formalizing this much more carefully in a bit. Exactly. Perfect. Now this gamma here, this is going to end up being the stack's contents. So we're going to be reading that again by convention from left to right, where the left side is the top of the stack. As we move to the right, we move to the bottom of the stack. So what do I mean by consuming a symbol? We're going to describe this in terms of a move. So to consume a symbol A, now keep in mind that we're also going to allow A to be epsilon. What this means is to go from one ID to another for the PDA. So suppose I give you a transition on delta here of P, A, and X. Remember, P is a state, A is an input symbol, and X is going to be the top symbol on the stack, right? And suppose this contains in its set of pairs that it returns back, Q, comma, alpha. So the way I would describe a move to you is if I consume symbol A, what happens is I can go from state P, where I consume symbol A, and this is the rest of W, by the way. This is like the rest of the string. So what I want to do is I want to gobble up like a hungry hippo. I'll just come over there and I gobble up this A. What I do as a consequence of this is I replace the top of the stack here with alpha. So what this symbol here is going to represent is move. So I move from one ID to another. So I went to state Q. I've consumed A, so notice A isn't here anymore. And I've replaced X with alpha. So note that B, you wonder if what gamma star is? That's just simply any number of symbols, well, stack symbols. So this is just a general definition for you. So when I use one of these instantaneous descriptions, you're going to find that I'm going to keep track of what the state is, what the input left I have, the stuff I haven't consumed yet, and also what's on the stack. That's all these instantaneous descriptions are. So don't let the symbols kind of spook you. That's all it is. So I want to just describe first, are we okay with this definition? I will be showing you some examples of using it, so don't worry. So I wanted to define one other thing. I also wanted to define something that's analogous to what we described for derivations for a context-free grammar. Because I would like some way to say that, okay, so this describes one move in the PDA. So I go from one configuration to another. We call these IDs. I go from one ID to another ID. So I would like some way of describing when I take multiple moves, like 0 or more moves. Just like when I had the context-free grammar, I want to be able to say I derived or replaced some symbols in the string. I want to go from one derivation to another, but I want to be able to do that and say, oh, I've done a whole bunch of derivations. So I want to do the exact same thing here. So I'm going to define this notion here, that we have this. But yeah, don't worry, I'm going to be doing a very lengthy example with you playing around with this notation. Just to give you an idea of what I mean by we kind of move from one configuration to another or one ID to another. So remember what I just described to you in that notation, that is going to be what we call a move. So I'm going to say, we can also define 0 or more moves. 0 or more moves of a PDA. So I'm going to use notation that's very similar to the one I used for derivations, except I'm going to use the same one I used for moves. So I'm going to add a little star on top of there, which I'm going to define inductively as follows. So which can be defined inductively. So just to reiterate, we can also define 0 or more moves of a PDA using that, which can be defined inductively. That looks like a very sad E. Let's try that. So here's how I'm going to define it for you. So first, I want to be able to describe to you if 0 moves happen. So I just stay where I'm at. So if I give you some ID I can indeed stay at my ID if I make 0 moves. So this is true for every instantaneous description I. So this is for 0 moves. That means I haven't done anything. So here's the way I'm going to define it inductively. So I moves to j if there exists some ID k so that I moves to k and k can move to j. But I naturally use potentially more moves. So if you're wondering what I mean by this, I'm just using essentially a transitive property. So just to be clear what I mean by this, i.e., just to elaborate on this, I moves to j if there is a sequence I1, I2, I3, all the way up to IN, so that I is equal to I1 and IN is equal to j. And for each, I is equal to 1, 2, all the way up to n minus 1. I, this gets a little fun, lowercase I, it moves to I subscript I plus 1 is satisfied. So this is just a way of me saying you move more than once, potentially. And all I'm saying is that there's a chain of moves that had to happen to get you there. So just remember, all I'm doing is going from one configuration of the machine to another configuration of the machine. So this is just a nice analog to our derivation idea we had for context-free grammars. So what I want to do next, just to give you a flavor for how these IDs can be used, I'm going to just lay out one set of all possible executions for a given input of a PDA we did last day. So just as first, I'm going to give you an example where I'm not necessarily going to use this notation, but I'll use that in a moment. But I want to motivate why these instantaneous descriptions are very useful for us. So example, consider a PDA PPAL. This is from last day, if you're curious where this is from. This is from last day. With input where I give it 4 zeros. So just before we proceed, if I give you the PDA PPAL, now remember PPAL had a start state that happened to be Q0, and its start symbol was Z0, which is typical of our setup. So could somebody tell me how I describe the initial ID for this for PPAL when I give you input 4 zeros like this? So let's get the initial ID here. So what would I describe this like? So remember, the first one is the state, the second one is the input that's remaining, and the third one is what the stack looks like. Perfect. That's exactly it. That's exactly it. So Q0, then 4 zeros, then Z0. So notice that this is indeed the ID that we start off with when we start up the PDA. So does everybody understand how we got this? So these are our three, remember this is instantaneous description is a triple. It has three parts. It has a state, the input that is currently remaining. In this case, I'm just feeding the input right to the machine, right? And then lastly, this is the state of the stack at this time. And it starts off with Z0 at the top of the stack. That's our start symbol. So what I would like to do is I would like to show you how the PDA operates like a hungry hippo trying to gobble up as many symbols as possible using non-determinism. So let me do that. So let's do that. Now I will stress the camera does not want to deal with the hungry hippos, okay? So I must stress that this picture will be in the notes after class, so don't worry if it looks like a pain to copy it down. It will be in the notes. It took me a while to draw it, so I'm going to carefully describe this for you. Okay. So, anyways, here is actually all ways, so these are all the valid moves that the PDA can execute on input 0, 0, 0, 0. So remember the input W that we start off with is 4 zeros. So this is our initial ID. So that's the one that we start off with. And now I've drawn out every execution of a valid move. Now you might ask, Dan, what's an invalid move? It's simply one for which I didn't describe a transition to you. These, of course, would end up being your killed threads or whatever you'd like to call them, where the teddy bear just sort of just says, I'm falling off the bed. That's sort of what happened with that execution. So the idea here is just that I'm going to describe to you in this, so there is a meaning for the way I'm drawing this, but keep in mind, I'm not going to ask you to draw something like this for me. I'm just laying out all paths of execution or possible ways that this non-deterministic machine can indeed process all possibilities. So if you're wondering, as you go down, this is actually the number of moves. So I start up here, so 0 moves happen here, 1 move happened here, 2 moves happened here, 3 moves happened here, 4, 5, and 6. So let me walk you through this. So I want to be very careful about this because this helps build the intuition for how the PDA is going to process a string. So like I said, the PDA goes around like a hungry hippo gobbling up marbles. In this case, the hungry hippo is looking for W. So remember, in PPAL, we had it where we had 3 states. You had Q0, Q1, and Q2. In Q0, it pushed as many X's and Y's as possible onto the stack, wherever it read a 0 or 1. Now, to make this simpler for us to work with, here I've made it so it only reads a bunch of zeros. So it means it's only going to push X's onto the stack in Q0. In Q1, remember, this is when it's going to read off the remaining of the input, possibly. It may or may not. You're going to see how this plays out. And it's going to pop off the stack whenever it sees a matching. So if it sees an X, it's going to, if it reads off a 0, it consumes the 0, and then it pops off an X. If it was indeed reading a 1, it would pop off a Y. So that would be what Q1 does. And then, of course, in Q2, that is when we're saying, hey, look, there's no more stack symbols except for Z0 that's at the top of the stack. So I want to walk you through this. So I want to first draw your direction to this part, this general direction I'm drawing my hands down at. So here I want you to notice that here, every time I'm consuming one of the symbols, like I'm the hippo here. So I consume one of these every single time and I push it onto the stack, an X. So I push an X onto the stack every time I consume a 0. But I stay in Q0 here. So I can keep staying in Q0 consuming zeros. And that means I don't know, the hungry hippo like poops them out or something. I don't know. I don't know. Maybe I guess that's the case, that the hungry hippo eats the zeros and then poops out X's. I don't know. That's quite a visual. This isn't the kind of X's and O's I was expecting to play today. So let's see. So in this case, notice that the chain consumes zeros and pushes X's onto the stack. But notice that as soon as this happens, you'll notice that I get to this part here. Notice that every time the remaining string actually goes down until I get to epsilon. But you'll notice that for our PDA, there is a way for me to transition from Q0 to Q1 with the top of the stack as an X. So that allows me to make a move from Q0 to Q1. But notice that there are no other moves that I can take at this point. So essentially, this is like the hungry hippo runs out of marbles and starting to run around trying to find more marbles. So it's not too much different from that idea. So there are no more valid moves when I get here. That means that anything I do at this stage, it's like if the thread died. That's what happened here. The hungry hippo has to, I don't know, eat marbles another day. No, I don't mean that figuratively. It's just a hungry hippo. It's not meant to be a living hippo. It's just a fun game that people play to collect up marbles. That's from some period of my youth, I guess. So, anyways, the point here is that that's one way that the PDA could process these things, and that is indeed valid. That is something that the PDA can do. But also, the PDA could go from this ID to this one. So for example, here, notice that I don't actually consume the zero. Instead, I use the transition to go from Q0 to Q1. So I make a move from Q0 to Q1 while I don't modify the stack. So this is allowed to happen because, of course, I have even length palindromes. I'm allowed to have it so there's no symbols. So, of course, I move the Q1 and then I go to Q2, but notice there's nothing I can do here because there's no X's or Y's. So I could go right to Q2 here, but notice, I haven't consumed all the symbols, so this thread, it's caca. It's not good for us. So both of these were caca. We can't do anything with those. So far, is everybody following me? So I'm just laying out all paths of execution of our PDA. And I'm showing you that each one of these is actually going to fail except for one. So same idea here. Notice that I can consume one of the symbols. I push an X. And then I can move actually to Q1. And that's when I can pop off an X by consuming another 0. But notice that, I don't have any more X's. But I can transition to Q2 because notice Z0 is the top of the stack. But I haven't consumed the whole thing. I haven't eaten the whole pie. So, caca, that's not good for us. That's not good for us. Next, notice that I could potentially consume, I don't know, let's go a little bit further down first. So suppose I'm here and I consumed 3 zeros, so I have 3 X's. It's quite an extreme move. So what happens here is I go to Q1 and then I consume the 0 and I end up only with 2 X's here. This one isn't good. Caca. I don't like that one. The PDA just didn't find a way to accept that path of execution. So what happens is now I'm going to take this route where I've consumed 2 zeros. So I'm going to transition to Q1 here. So the PDA moves the Q1. And now what it's going to do is I'm going to consume one of the zeros. That means in Q1, I'm going to pop an X. And then I'm going to consume another 0. I pop an X. So now I have no more symbols left in my input. And it's Z0. But luckily, I have a transition that gets me from Q1 to Q2. So I make the move from this ID to this ID. But the great thing is Q2 is a final state. So that means that for this ID, we accept. So you might ask, Dan, how do we know the machine rejects? Well, it has to go through all possible ones of these valid moves. And it has to say, hey, look, there is none of them that are going to get me so that I consumed all the symbols and I'm in a final state. So does this help a little bit with the idea of how these IDs describe the machine? So when I have my machine, I have some input. This describes all possible ways of I can look at all of the IDs. So these are all possible ways that the IDs can move from one to another. Yes? Sure, this part right here, like where I go from, say, Q0 to Q1 right here, like that. Oh, it's 2-1 to 2-1, let me see. Okay, from move 2 to move 3, which column are we looking at? Here? Second column. Okay. So I must stress that the arrows are what you should be keeping an eye on. So when I move, I'm moving along these arrows. These arrows are just to help me visualize the execution. So when I go from here, there is no arrow here. This ID comes from this one. So when I move here, so what happens here is all I've done is I've used an epsilon move, hence why we call it an epsilon move. So I've used an epsilon move from Q0 to Q1, and that move is allowed because remember in PPAL I had a transition. Well, I'm allowed to move where I have epsilon, and then I can have it where the top of the stack is in fact an X, and it just keeps it as an X. That's what's in PPAL. So that's what happens, how I get from Q0 to Q1. So it's an epsilon move that's happening. That's why you'll notice I don't gobble up any symbols. I use an epsilon to do this. So whenever you see like, okay, well, like, how did you go from this state to another state? But so like this one, for example, like when I have Q0, 0, 0, 0, X, Z0, you'll notice I go to Q1 and then I have the same symbols here in the input. And I also still have the same stack. That's an epsilon move that's happening here. Because remember, I'm allowed to have when I describe my IDs, I'm allowed to have it so that the symbol consumed is epsilon. I'm allowed to do that. So sometimes I may not consume an actual symbol from W. Instead, I may actually consume an empty string. And that's usually a mechanism you can use to go from one state to another state. It's often a really nice feature. But does that clarify things here? Hey, no worries. No, sounds great. Okay, so now I want to do one more example just to illustrate my point here. So let me move on over here. So I had to show you the dramatic picture. So I want to show you a usage of this notation. So I want to show you how you can use the notation. And it's actually really useful in some aspects because if you want to describe what the PDA does, these moves, just like when we do derivations, they describe something quite like what I have over there. You remember we have those parse trees? So remember when I drew a parse tree, like, okay, well, it's all these steps I do, just like I had over here. So it actually has its own usefulness as well as a set of notation. So here's just another example. So suppose that the input is, say, 1, 0, 0, 1. So just as an example, we already know that the input better look like this. So this is this is our first ID that we have. Now, of course, I can consume one of the symbols. So I can consume the 1, and then I can push a Y onto the stack. So that's one thing I can do with PPAL. So keep in mind, this is for the same PDA. This is for PPAL from last day. So remember, when I'm in Q0, I can gobble up zeros and ones. And whenever I have a 1, I'm going to push a Y. Just like before I had a 0, I can push on X. So I can push an X. So keep in mind I could keep doing this. So I can take Q0 and I can consume a 0. And then I end up with X, Y, Z0. I can do the same thing. Actually, instead of doing that, let's transition over to Q1. So let's make a move from Q0 to Q1, which I'm allowed to do because that is indeed an epsilon move. And X or Y is okay to be at the top of the stack. In this case, I have an X on the top of the stack. So next, all I'm going to do is I'm going to gobble up something else. So let me see here. I'm going to gobble up a 0. So let's gobble up a 0. So I better put a 1 right here. So my PDA as a hungry hippo eats up the 0, and then there goes X, and then naturally I can consume. Well, I can't. The hungry hippo, or PDA, does. Can gobble up the Y. But now notice that now I have it so that I'm in an appropriate state to get me to Q2, so I'm in the appropriate configuration to do that. So what I'm going to do, so let me see. So we gobbled up the 0, we gobbled up a 1, and now we have this. So I'm going to just transition into Q2 on epsilon, Z0, and this indeed, like this indeed tells us that this is going to accept the string W. Do you see how we can use the notation? So this is just me describing to you different moves that you can make. So this is just one path in the example I did over there, except this is just with a different input string. I encourage you, if you're really just not seeing what I'm saying, just take a look after class, take the input with the 4 zeros, and try this exercise of getting yourself to the accepting state that we had in the previous example. So a more brief way I could describe this is I can just go Q0, 1, 0, 0, 1, Z0, and I can go, it moves to Q2, epsilon, Z0. So this is the shorter way I could describe everything I just did right here. But it's very much like when you're writing out algebra. You want to make sure you illustrate these most important parts of this process. So I just want to do an example just to illustrate this idea for you. So just to illustrate this idea, I want to convince you that this notation actually can be pretty useful for checking if a PDA makes sense or not. So just to illustrate this, keep in mind that this would be one direction in a proof of correctness of the PDA, if you're just curious about that fact. So I'm going to say, notice that a p-pal with p-pal, whenever we are given a string of the form WWR. Remember, when I use this R like this means reversal. And we push X's and Y's corresponding to W. I'm going to call it called Y. I'm just going to call that Y to make this a little easier. We can see WWR gets accepted by PDA p-pal. So I'm just going to give you one. So this, I want to reiterate this. This is one direction in the logic of proving that this PDA actually works the way you want it to. So I want to illustrate this direction. The other direction would be that you describe from the PDA standpoint how you show that WWR is in fact going to get accepted. So you do it from the PDA's standpoint. You start at what a final state would mean in that PDA, and you kind of work your way so that you show that the string has to, like the string that you get after you accept has to look like this. So I just want to show you kind of how you can go one direction in this proof using this notation. So here's a way I can use the IDs to help me do this. So I like to think of it almost like you're doing some algebra. So I'm going to make a series of moves. What I'm going to do is I'm going to consume the first part of the string, the W component. And that means I'm going to end up with Y. So Y is going to be in reverse because it's a stack. And then I can make a whole bunch of moves again. I can make a whole bunch of moves again where I take, let's see. Of course, once you're in Q1, because remember, once you're in this state, what you do is you can move the Q1 and then you can gobble up the rest of the string. In this case, it's WR. But remember, WR every single time is going to match up the X's and Y's respectively with zeros and ones. But they're going to be given to you in reverse, which will be perfectly fine. Which means you'll end up in this state. Sorry, this configuration of the machine. And then you have it where it's sitting like so. Or it's in Q2, just like we had in our examples. So notice that using the instantaneous descriptions and this formal notion of a move, I can describe to you in a nice, elegant way how the PDA actually does indeed do what I say it does. Does everybody see that? Is that kind of clever? So this notation is pretty helpful. It's kind of like doing algebra on a machine. I don't mean on the machine. I mean literally of describing the machine. It's kind of meta like that. So it isn't like calculating what the square root of like 4 is or something. This is me describing the machine's moves to you. So this is the analog to our extended transition function, by the way, if you're curious. So you might naturally ask, okay, well, how do we define the language of a PDA? So I've given you all the pieces that we need to get there. So now, this is the weird part about PDAs. Just to be clear, there's a lot of things I can talk to you about PDAs. Like, I can easily spend at least another couple weeks talking about PDAs. But unfortunately, because we have so many things we need to talk about in this class, I'm going to just keep it a little bit briefer here. So a PDA, believe it or not, there's actually a couple different equivalent ways you can define acceptance for a PDA. So up to this point, you've just assumed that, okay, well, I gobble up all the symbols, so all those symbols get consumed via moves. And if I'm sitting in a final state after I'm done this process, that means that the machine has to accept. That's what we've assumed, right? We've assumed this. But believe it or not, there's actually other ways to characterize how a PDA can accept. That's actually one that I won't necessarily have time to talk about here, but I'm just going to allude to the fact that it exists out there. But let me define the language of a PDA in the following way. So I'm just going to mention that there are a couple different ways to define acceptance of a PDA. And I must stress that they're all equivalent. So this is a little different than the other examples we've seen in this course. In this version, there's actually a couple different games you can play for your PDAs. So the one that I'm going to be focusing on is acceptance by final state. There's another version called acceptance by empty stack. So I'm going to focus in on acceptance by final state. There exists this other version where what you do is you play the game of you don't care about final states anymore. Instead, what you do is you look at if the stack is empty or it isn't. And if the stack is empty and you've consumed all the symbols, that means that the machine accepts. So that's how a PDA where it accepts via empty stack works. But that is not the rules that we're going to follow here. We're going to follow the one that we've been using this entire time. So we're going to be looking at, we will talk in terms of acceptance by final state. So if you find yourself curious about this empty stack business, the Hopcroft book does a very good job laying out this, and it actually gives you the proof for the equivalency of these. You'll find that actually in the Pushdown Automaton chapter if you find yourself curious about it. I'm not going to require you to know about that. I just want you to just be aware it exists. Sometimes it has its usefulness. Okay, so here's how I'm going to define a language of a PDA. So I must stress, this isn't the only way I can do it. There exists this other way I can manifest the acceptance of a PDA. But I must stress, even though they're equivalent in their conception, the PDAs actually look different. I must stress that. Language of a PDA. So consider any PDA P. The language accepted by P So I got to write out all the tuples. Q, sigma, gamma, delta, Q0, Z0, F by final state. So just to be clear, final state, this by final state is exactly what we've been doing this entire time. By final state denoted L of P is the following. So the language of PDA P is equal to the string W such that Q0, W, Z0, it eventually moves to the following ID. QF epsilon alpha. And you might ask what that is. That is where QF is in the set of final states. And the great part is that alpha is any stack string. So we don't really care about what's on the stack at that time. We just care that all those symbols better get consumed, and you are in a final state when that happens. So that is the definition that we're going to use for a language of a PDA. So unfortunately, I ran out of time to talk about the example I wanted to do today. So instead, what I'm going to do is I'm going to ask you to take a look in the notes at this example. It's actually it's almost identical to the kind of stuff we were doing last day. But I wanted to show you a neat trick of how you can combine smaller PDAs to make a more complicated one. So in this example, if you find yourself curious about it, the PDA in particular was for the following language, which is kind of... So I'll ask you to read this. So just read example, and this is the language that it's about. It's A to the I, B to the J, C to the K, such that I, J, and K are all non-negative, and I is equal to J, or I is equal to K. So this is a nice classic example of illustrating the technique I was talking about at the beginning. So if you're wondering about this, the way it works is that you design a PDA where you take I is equal to J. Then you design a PDA where I is equal to K in this. And you'll notice that these are actually very similar to the ones that we did actually last day. So the cool part about this is that once you have two PDAs, so for example, if you have one PDA that looks like this, another PDA, so suppose I tell you that the PDA for which this is satisfied is called P1, and the one that's the other PDA has this condition in place, and you require that at least one of the two is satisfied. What you could do is you could take a new start state, I'm going to call that Q0, my apologies, and say this is PDA P1 and that's PDA P2. It'll have its own final state somewhere in here, but the idea is it'll have its own start states. So what you do is you just simply introduce epsilon moves, where each one of these moves that are made will be done on epsilon. It's on epsilon, and it's just going to observe that the stack just has the start symbol on it. So this will be the case for both of these. So if you look at this carefully, I just want to point this out before we go, is that notice that if I do this, I can just take an epsilon move, and that'll allow me, because of the non-determinism of the machine, allows me to go into P2 and also into P1. And then they're going to try to consume the strings on each of its own simpler PDAs. But remember, these PDAs they're still just parts of our larger PDA. So is this kind of cool? So what you could do is you could just make epsilon moves from each one, and you just don't push anything onto the stack or anything. And you just let the PDAs take care of all the work. So you just design some two simpler ones, and then you can put them together using epsilon moves to make a more complicated one. So I'll ask you to take a look at that in the notes. But this is the core idea, is that whenever you see something like an OR like this in a criteria, think about what the languages actually mean. That's the biggest tip I can give you about designing machines like these, is look at what the definition says. And if you look at, well, if I is equal to J, for example, that means that this is like no different than if it was A to the N, B to the N, and then this C is allowed to be whatever you like it to be. But we did an example literally like that last day, except the only difference is we have to allow there to be, allow there on the final state of our example, actually last day, we allow it to gobble up the rest of the C's by making all of those valid moves. So that being said, we're going to stop right here. When we come back, also I want to apologize for going over by about a minute or two here. When we come back, we're going to start looking at properties of context-free languages. So I want to say thank you very much and have yourself a beautiful day. I'll see you later.